When we deal with proportions, proportions are just success rates. We saw them in binomial distribution when we looked at how many successes we could get from a certain size trial when we knew our success rate, our proportion, that's P. So this was binomial information, the mean and the standard deviation. That helps us to be able to analyze sampling distributions of proportions. If the true proportion is right here, when we take samples, we get some fluctuation due to random chance. That random chance is expressed with the standard deviation of the sample proportions right there. So we get this distribution of sample proportions. We use these distributions of sample proportions to help us do inference on a population proportion, either confidence intervals or hypothesis tests. Suppose that 15% of motorists are uninsured. If we randomly sampled 270 motorists, find a probability that at least 12% are uninsured. We know that it's okay to approximate this discrete distribution of sample proportions with a normal distribution if the expected number of successes is at least 10 and the expected number of failures is at least 10. It's good to know that in reality, sample proportions have to be discrete. If we took a sample of 270, you'll get anywhere from 0 successes, which is 0% success rate, up to 270 successes, which is 100%. But there's only 271 possible sample proportions you can get. So in reality, that's why I say the distribution is discrete, but we can superimpose a normal curve over what would otherwise be a bar graph of proportions by knowing that these two things are true. If those are not true, we have a skewed distribution and we have no business being able to superimpose a normal to approximate. Again, if we don't fully understand that, we're okay as long as we say, hey, we obey the restrictions or the requirements, the assumptions for normality by checking that the expected number of successes and failures are both at least 10. So, in our situation we just talked about, we have this sample size. We're assuming the population proportion is 0.15. What's the likelihood our sample proportion would be at least 0.12? There's our sampling distribution of proportions. Our success rate is that right there. We can use a z-score to tell us where we are in this normal curve, with that many standard deviations to the left of the mean proportion of 15%. We can use the normal CDF and just type in the z-score from negative 1.38 under the curve to a big z-score, and that standard normal distribution has a mean of 0 and a standard deviation of 1. That is how the z-scores are distributed. We get that result from the calculator, and that's the answer to our probability question. 91% of all samples should be returning us a situation where we have at least 12% of the motorists uninsured, as long as the population proportion is accurate. Well, we use that understanding of probability to do things like estimate the proportion of US AP statistics students who will get less than 6 hours of sleep the night before their next test. We randomly select 30 students, we hook them up with the sleep detecting electrodes, and we find that 25 of them get less than 6 hours of sleep. But hold the phone. We made a boo-boo. We realized that because the sample size was so small, 30 is okay if you're dealing with sample means, but remember, we have to have it so that n times p and n times 1 minus p are at least 10. N times p is our successes, n times 1 minus p is our failures. So we got 25 successes, but in a sample of 30, that means we only got 5 failures. That's no good. We would actually have a skewed distribution in reality. We can't do a confidence interval on this situation. So we abandon the electrode thing, which is a bad idea anyway, and now we're going to take a sample of 165 students, and let's suppose that 78 of them got less than 6 hours the night before their last exam. So we wish to construct a 95% confidence interval. Now here, when you're taking an AP exam and a free response question, the prepositional phrase, that's right, we're using language arts in here, but the prepositional phrase will actually describe the parameter that we're estimating. So we're doing a 95% confidence interval for the proportion of US AP Stat students who got less than 6 hours of sleep the night before the last test. So they give it away. They tell you what the parameter is that we're estimating. We go to a sampling distribution and proportions. Again, with the confidence interval, we don't know what the true parameter is. What, in this case, what the true population proportion of all US AP students is with regard to how many of them got less than 6 hours of sleep. But we know where that parameter goes. It goes smack dab in the middle of a sampling distribution of possible proportions. So that's theoretically what should happen. Where would the middle 95% be? Well, we know from doing this that if you go 1.96 standard deviations in each direction, you'll trap the middle 95% of all sample proportions. Therefore, 1.96 standard deviations is the margin of error that we have to go in each direction to trap the middle 95%. On our formula sheets, we see that we take our statistic plus or minus critical value times standard deviation. If we can understand that the population parameter is a population proportion, then we know that our statistic from our sample is a sample proportion. And we can go to our formula sheets, our AP Stat formula sheets, to let us know what the standard deviation is for a single sample proportion if we don't remember it. So we put that there. So plug in all the numbers, and then we get our confidence interval, and the last thing we have to do is to interpret the interval. We're 95% confident that the true proportion of all USA AP statistics students who got less than 6 hours of sleep the night before their last exam is somewhere between about 39.7% and about 54.9%. Then we can do inference on testing a claim. Suppose a college admissions officer claims that 80% of incoming freshmen are using student loans to pay for the majority of their college costs. Random sample of 233 incoming college freshmen was taken. 170 are using student loans to pay for the majority of college costs. When you see the phrase similar to this one, is this evidence to suggest, that is a tip-off that we are to write a 5-step write-up and do a test of significance, a hypothesis test to test the claim, and the claim is regarding the proportion of students, of incoming freshmen, who are going to use student loans to pay for the majority of costs. So we need to do a 5-step write-up. First, we name the test. It is a t-test, and we describe what claim and what parameter we're testing. So it's claimed that 8% of incoming freshmen use student loans to cover the majority of college costs. I tell my students to name the parameter right here. You don't have to. You can do that at the very end when you're summarizing and you're concluding. It'll save time. But it's nice to know and tell the AP reader right up front, hey, I know exactly what I'm talking about. I think it may bias them towards liking you that you have your act together, just a personal feeling. Then we say we write down the claim. The claim of the counselor or the admissions officer was that P was equal to 0.8. We write the complement down. This one has the condition of equality, so it's the null. There's the alternative. Note that it's a two-tailed alternative. We're going to have to double the area under the curve to get our p-value. Get to that in a minute. We have to address the assumptions. That's the third thing. SRS, we were told in the problem that it was a random sample of 233. Make sure you're verifying the assumptions are met. Don't just say SRS and put a check mark. We were told that it was a random sample of 233. Normality, we test for normality with proportions, unlike with sample means, by taking the expected number of successes, the sample size times the assumed proportion in the null. Always assume the null is true. That gives us 186.4 expected successes. So the number of failures, n times 1 minus p, would be 233 minus that many successes, so that would give you 46.6 failures. I just point out that the failures and the successes have to add up to the sample size. You can go ahead and just take 233 times 0.8, don't get fancy, write down the 46 failures, that's fine. We also need to know that the variance is trustworthy. We should never take a sample size that exceeds 10% of the population size. So just multiply the sample size by 10. As long as your population's at least 2,330, you're good to go. And certainly incoming freshmen in the US, there's millions of them, so a lot more than that. So we're okay with the assumptions. Then we go to show the work. We show that our p hat is right here, our sample proportion. We assume that 0.8 is true, that the null is true, and that's what we put in the center of our sampling distribution. And we go find the likelihood of getting a result at least as extreme as the one that we got. So we use the z-score formula. Again, we can follow the formulas that are on our formula sheet as far as how to find the test statistic. You can look at the video on means if you want to. But at any rate, we plug in all the numbers where they go. Don't forget that this has to be the P of the null. It's this sampling distribution for which we need the standard deviation, not some sampling distribution that would have that as its mean. This is just assumed to be one sample result out of this sampling distribution where the null would be true. We're still assuming the null is true until there's enough evidence to reject it, and it's coming. So anyways, we get a z-score of negative 2.68. That's pretty extreme. We're over 2.5 standard deviations below the mean. We find the area under the curve. It must have been 0.0035. Let's face it, we can use the z test, one proportion z test in our calculator to get the z-score, to get the p-value. We can pretend that we did it on our own. The calculator will automatically double the area under the curve because now we're assuming the null is true until the very end of the process, so if the null is true, how often would we expect to get a result at least as extreme as the one we got way down here on the left? Answer, 0.0035. But hey, if it all happened due to chance anyway, and that's what we're still assuming, that the null is true, and this result's happening due to chance, then it could have just as easily have occurred as many standard deviations on the right side also having this probability. So the reason we doubled the area under one tail is because we're still assuming the null is true. We're pursuing the possibility that this extreme result just happened due to random chance. So there's our p-value. That's the probability, an estimated probability of making a type 1 error. So because the probability of a type 1 error is less than 0.05, we reject the null, and then we have to go and put it in layman's terms. What does that mean if we reject the null? It's not very nice. How does we think it makes the null feel? So we say it in a way that others can understand. We say, hey, the evidence suggests that the officers claim that 80% of incoming freshmen use student loans to pay for the majority of college costs is incorrect. Whatever your conclusion is, rejecting or failing to reject, I suggest you go back to the alternative hypothesis. The alternative hypothesis, in this case, was that the officer's claim was incorrect, that the proportion was not 0.8. So we would say the evidence suggests that the proportion is not 0.8, that it's not what the officer claimed. If we were to fail to reject the null, I would suggest still coming to the alternative and saying that the evidence failed to suggest that the true proportion was anything other than 0.8. It's just a nice way to make sure that we're not getting tongue-tied and saying things incorrectly. So there is the progression from sampling distributions of proportions to inference, confidence intervals where we estimate the proportion, and hypothesis tests where we test a claim.